This is the solution to the SHM Basic Spring Graphical 11 mark question. That's the January 06 question 3. Starts off with define simple harmonic motion. Well, that's where the acceleration is proportional to the displacement from the equilibrium position, and always directed towards the equilibrium position. So, acceleration proportional to displacement from where and direction, and being really specific that when we say towards it, we mean towards the equilibrium position. I wouldn't say towards it. You're making an assumption that the examiner will believe that's what you mean. So, there's the definition of simple harmonic motion. The curve labelled x shows how the acceleration of a body executing SHM varies with time. Add to the graph a curve labelled y showing how the displacement of the same body varies with time over the same time interval, and a curve labelled z showing how the velocity of the same body varies with time over the same time interval. So, we have already said acceleration proportional to displacement and always directed towards it. Hopefully, you're remembering that a is minus omega squared x. It is minus some constant times x. And so your curve y is going to be down here. It's going to be a minus x curve with some scaling factor omega squared. So that's going to be y. Z then, the velocity, well, you have to think, what's the velocity doing? When the acceleration is 0, that's when the object, whatever it is at its maximum velocity. So at all these points of 0 acceleration, 0 displacement as well, it's going through the center of oscillation at these points, and that's the point at which it's traveling at its fastest. If you think about a mass on a spring or a pendulum, you'll see that that's the case, although we've already established that in our setting up of SHM notes. So the maximum velocities will be here, 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 and here. So when the acceleration is a maximum, well, that's when your oscillating body is changing direction. So that's going to be when the velocity is 0. So the velocity will be 0 here, 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 and here. And then you have to say, well, okay, I know I'm going to have a maximum velocity here, but is it a maximum positive or a maximum negative? So if you think about your mass on a spring, let me just bring this in here for you. Here's my t equal to 0. At some time later, it's moving down at this point. At some time later, it is below the equilibrium position. So the acceleration is up and the velocity is down. So here we have a positive acceleration, like we have here, but the velocity is negative. Quarter of a period, it's at the bottom. It has stopped, but the acceleration is a maximum here because it's at a maximum displacement, of course. So the velocity is 0, maximum positive acceleration. Here we're back to the equilibrium position, x equals 0 at 1/2 period. So the acceleration is 0 because it's going through the equilibrium position, x equal to 0, and a is minus omega squared x. And here the velocity is a maximum. So thinking about all of that, what our graphs will look like is very much like that. Oh, that didn't work. There we go. So that's what the graphs will look like. There's my graph of displacement. There's my graph of velocity. So there it is. Finally then, we have a mass of 150 grams supported by a spring having a spring constant of 24 newtons per meter, show that the frequency of vertical oscillation of the mass is about 2 hertz. Well, we know from our earlier work that T is 2 pi root m over k. If we stick in our numbers there, we get square root of 0.15 over 24. Of course, we know that the frequency is 1 over the period. And if we do the numbers there, then we get 2.01. And to 1 sig fig, that is 2 hertz indeed. To 2 sig figs, it's 2 hertz. So there it is. And then it says the amplitude of oscillation is 30 millimeters. Calculate the maximum speed of the mass. So we're going to use our V is 2 pi FA expression. And we're going to stick in our numbers, remembering that our A that we're given is in millimeters, so we want that in meters, 3 times 10 to the minus 2. I'm using the 2.01, but actually, because it's 0.01, it's actually not going to make a difference to my answer to 2 sig figs. So I could have just used the 2 and ended up with the same answer. But it's good practice to use the greater sig fig result and to round at the end, because very often it will make a difference. And so finally then, the answer is 0.38 meters per second, and I'm checking the sig figs, got a couple there, I've only got one there. So we should probably give it to 2 sig figs, 24 newtons per meter, 30 millimeters, 150 grams, 2 sig figs, 130 meters, or 0.38 meters per second.